Hello again.
Hello, good people. This is the rest of Chapter 9, talking about effect sizes of a one sample design t-test. So some of this is going to be review for null hypothesis testing, and we're going to get into the specifics of the Doritos example in the one sample, and then we're going to talk about effect sizes for what you should be finding out every time you do a t-test anyways. So again, this is review from null hypothesis testing. U sub 0 is the claim of the population, and U sub 1 is the unknown true population mean. You assume that what they claim, so if we want to go back to the Doritos example, they claimed that 263 or whatever, 269, 267, whatever that was, they believe that's what they're equal to what the unknown true population mean is, but you did your own sample. I think it was they bought 8 bags of Doritos, and then they came to their mean, and they want to find out if they are equal to each other. So again, we start null hypothesis testing with the hypothesis of equality, the null, symbolized H sub 0. The alternative hypothesis is typically that they're not the same. Got to review this again. That means either one could be, they could be different in either direction. One could be lower, one could be higher. So that's why you got to pay attention to this direction of which one you think is going to be higher, which one's going to be lower, because that's going to play into how we deal with our P05 level. So again, review again. We start assuming that the null is correct. Take some samples. If you know you're taking some samples, you're using the t-distribution. If the probability of your sample, of getting that sample given the true population average is correct, if that probability is high, we accept the null. What does that mean? Again, if we go back to the example of shoe sizes, so if you got 9 is the true mean, you take a sample and you get 8.5, that's pretty close to 9. Probability giving 8.5 given that the real average is 9 is still pretty high, so that means we accept that 9 is the real average. Let's say we claim that the real average is 9, but then we get a sample of 6. That's the likelihood of getting a sample of 6 is pretty low. So if it's too low, we get to reject the null. That means we get to reject the idea that the sample is that the true average is 9. So what value is small? Again, we talked about this before. It's widely accepted as 0.5, not entirely accepted, but I'm sure you can Google that somewhere else on your own time. We talked about this in the early part of Chapter 9, the rejection region. If you're drawing it, that's the part that you reject. It's going to be toward the tails on either side. The critical values are going to be the values in which you figure out if your t-value is beyond or in that rejection region. So we don't need to construct an entire sampling distribution each time you want to test the hypothesis. So what does that mean? That means we can just use a t-distribution. So we got to use a one sample t-test. So this is the most simplistic t-test that's out there, one sample. Why is it called a one sample? Because we're only taking one sample, even though you took 8 samples theoretically. You took 8 bags of Doritos, and you took the average of all those things, so you're using that as a sampling distribution, and that your average was what you got from those 8 bags. When you said one sample, you're comparing it to something that's been claimed. So somebody else is giving you that information, somewhere else that information is coming from. So you're only taking one sample, you're comparing it towards something else. So here on the bottom, if you look, we got a t. So how do we get our t-value? We take the average of the samples, like the x bar, and you subtract it what the claim is. So in this Doritos example, again, it's the average from our 8 bags subtracted from what Frito-Lay claims is in all the bags, divided by the standard error mean sample. So how do you get the standard, I'm sorry, not standard mean, standard error of the sample? How do you get the standard error of the sample? Well, you calculate this standard deviation of the sample with S hat, the n minus 1 kind of stuff, and you take that and use the denominator of the square root of n. So in this case scenario, or n, or sample, we're talking about the Doritos again, we had 8. So our degree of freedom is 7. On our sample over here, we're trying to calculate the standard error. We need to use the 8 there. So again, let's go back to this Doritos example and be more specifically. So you've got the average, so our average of 8 bags was 270.675, whereas they claimed it was 269.3. Got our degrees of freedom of 7, talked about that before, our N was 8 minus 1, so that's where we got the 7. S hat, again, you should look it up in your homework if you're going to find it. It'll be given to you on quizzes, because we're not calculating that anymore, so you've got the S hat over here, 0.523. You put that into the equation with the denominator, the square root of 8. You get the standard error of the sample, 0.1849. Again, this is all just sort of algebra. So what do you do here? You plug it into the equation here. So you got that 270 subtracted from 269. You take all that and you divide it by standard error. That 0.1849. You get a t-value of 7.436. So this is our t-value of this sample. So it's sort of like a z, but it's not really a z yet. It's just a t. So we're going to be plotting it like we were on a z. We need to figure out where that t-value lies. And so here's what you need to do. You look at the table D, appendix C, and you find out. Again, we assume using we start with the 0.5 level. That means we got a 95% alpha level. Or I guess it's really bad, but the alpha 0.05, the opposite is 95. So if you're looking for a significance value of 0.05, you look up your critical t-value. How do you do that? You go to the 0.5 two-tail test, 0.5, go to the degrees of freedom across over 7, and you get that number of 2.365. So if you're going to draw that on a data distribution, you would draw that and say, all right, it's almost like standard deviations. You put a 2.356 right there and say, all right, that's the 0.5 level. Then you go out to the 0.1 level, which is the opposite of 99. So you got the 0.1 level, 3.499. So again, you're still at that degrees of freedom 7 column or row. And then at the 0.01 level, you've got a critical t-value of 5.408. So what does that mean? If you're going to plot it, if you're going to draw it, you have that 2.365, and then more toward the extreme, in either direction, the right or the left toward the tail, you have 3.499 for the 0.1 level, and then the 0.01 level, you'd have a critical value of 5.408. So what you want to do is you want to sort of think about and or draw where those things are, and then figure out where your obtained t-value is. The t that you obtained from doing your calculation right here was 7.436. So if you're going to put it on that data distribution, it would be beyond that 5.408. So I mean, it's really deep into that tail. You're talking about the tail on the very far right. So we are way into the designated rejection region at this point. We are way less than 0.5, we're less than 0.1, or we're less than 0.01 because we're beyond 5.4. So again, that's what we're looking for, is where does that t-value fall relative to these critical values. More will be shown in the video of how to do this using the worksheet. So if you find a critical value beyond any of those areas, the 0.5, the 0.1, and the 0.01, this is what you're able to say. So I need you to sort of memorize this. Remember, this is how you interpret this kind of null hypothesis test. You could say that the mean weight of the 8 Doritos bags was 270.675, which is significantly greater. It's going to tell me that it's greater, so you can tell me the direction, than the company's claim of 269.3 grams, p is less than 0.001. So the probability of getting that sample, 270, the probability of getting that sample given 269.3 is the correct average, is very, very improbable. So that's a very, very low probability, so it's less than 0.01. So what does that mean? That means we reject that they're the same. We don't say that these are the same. So theoretically, the student was sort of correct. The student was saying, you know what? I don't believe what's claimed on this Doritos bag. The issue is that I'm assuming this student thought it was in the other direction, that they were getting gypped. This is saying that they are significantly greater than what's in the bag. So the student actually got more Doritos than what was claimed on the bag, significantly greater than what was claimed in the bag. So that's what this is sort of talking about. So look at the very bottom here. Note this hypothesis is testing a sample against a claimed population mean. So this is the most simplest form of hypothesis test. So if somebody gives you a population, you take a sample, you compare it to something that's claimed. That's the most simplest. Why do I mention that here is because we're going to get to two sample t-tests. So that's going to be more common. It's basically like, oh, I've got one stats class over here that I gave one exam to, and I've got another stats class over here that I gave a different stats exam to, and then I've got two averages, and I want to compare to each other. That's a two sample. I got two different samples. This is just if I take one sample and compare it against another population mean. And so I do want to mention this idea of a one-tailed versus a two-tailed test. If you notice at the very top of Appendix C, Table D, across the top it asks, are you talking about a one-tailed test or a two-tailed test? So the Doritos example we've been using so far is a two-tailed test. And so what does that mean? It sort of means that the obtained sample average can be statistically significantly different from the claimed population average in either direction. So you're allowing it to be very, very low or very, very high. So that's why you get to use both tails. So if you do that, you're able to use both of those tails. So in this scenario for this Doritos, this person doesn't necessarily have any scientific evidence or hypothesis or theory to support this person's idea that they got gypped out of Doritos. All they're saying is that I just don't believe it. So like we mentioned before, we had this idea that it can be higher or it can be lower. That's what makes it a two-tailed test. If you have, so this is the Doritos example that we've been talking about, but a lot of times in research, you've got a one-tailed test where I'm only interested in the samples different in one direction. Most applied research is going to be doing that because, like for instance, you see this sub-bullet point, drug and decreases depression symptoms. You don't assume that you're creating a drug that's going to increase depression symptoms. So what does that mean? You only care about decreasing symptoms. So all you really care about is seeing if your drug, the sample that you get from your drug, is statistically significantly less than what the average is. So what does that mean? That means you get to take all that 0.5 probability and throw it under one tail. So it's a little different. You get to play in a bigger sandbox of 0.5 in one tail as opposed to having to split that 0.5 in a two-tailed test. So what does that mean? In a two-tailed test, you got to take that 0.5, you got to split it, and you split into, you got 0.025 on one side, you got 0.025 on the other side. So it's actually more difficult to find statistical significance if you're using a two-tailed test, and that's kind of good because if you're using a two-tailed test, it kind of means you don't know what the hell you're doing. If you know what you're doing, you've got some theory, you've got some research to back you up, you should be using a one-tailed test, and you get to use all that 0.5 in one direction. So that's the difference when you're looking at Table D, Appendix C at the very top, your one-tailed versus a two-tailed test. We'll talk about it in the worksheet, and in your homework, it'll highlight, are you dealing with a one-tailed test or a two-tailed test? And so once you identify if it's a one-tailed or a two-tailed test, then you figure out which critical value, which column you need to look for your critical value to find out if your T is statistically significant or not. How are you going to be able to figure that out? It's going to be in the setup. They're going to tell you if the hypothesis has a direction to it. If the hypothesis is, I believe the training increases productivity, or the alternative hypothesis is that training increases productivity, or the alternative hypothesis says the drug decreases depression. That is a directional hypothesis, and so you should be using a one-tailed test. If you say, oh, I don't know, I don't believe that they're the same, then you have to use a two-tailed test. I think finally on here, effect sizes here again, we've already talked about this before. If I want to know the difference, the effect size of being in one group or the other, so of being in the claimed population, Doritos example, versus the actual sample, how big is that effect? Well, again, we're back to the 0.2, 0.5, 0.8, small, medium, large kind of stuff. So again, if you want to separate from people who really know what they're talking about in stats versus the ones who don't, you've got to ask about effect sizes. And so, sure, I found a statistically significant difference between 8 bags of Doritos versus a claimed population versus the 8 sample average way down. How big is that difference? You know what I'm saying? How large of a difference is that? So how large is this difference? So let's talk about this Doritos thing. So what do? We take our claimed population average, subtract away from the sample average we got from the claim, and then we divide by this as hat. And what do we get? We get an effect size of 2.692. And you're like, whoa, okay. If you remember from the previous slide, 2.629 is very, very large compared to the 0.2, 0.5, 0.8. So this would say that there's a large effect of the difference between these two averages. I don't know if, again, if this page is correct, it's 188, but it's around that page. We talked about this in class before. Sure, there's a significant difference in children's IQ if they participate in Head Start program versus not, but how large is that effect? Well, the sample, I'm assuming this is the individuals who went to Head Start versus the children average who do not, and you get an effect size of 0.3. So if you're going to interpret that, what does that mean? That the effect of Head Start is between a small and medium effect on whatever it is you're talking about. So it'd be nice to say the effect of Head Start is between a small and medium effect on children's IQ. So that's how you would interpret it. And again, we're moving in this class more toward interpretation as opposed to calculation. So spend some time thinking about how you're going to write and say these statements about how to interpret these things, how to interpret an effect size, how to interpret a statistically significant difference. That's what I'm going to spend some more time on.